So look at this problem here that is basically about basic trigonometry. They say for the triangle, what are the length of the unknown side? What is going to be the unknown side? Of course, this is the unknown side, x, because we know this side, that is 6 meters. We know the longest side, that is 9 meters. So we don't know the other shorter side. So we have to find the length of the unknown side. We have to find the tangent of zeta. Zeta is this angle. And we have to find the sine of phi. Phi is this other angle, right? So we have to find the unknown side, the tangent of zeta, and the sine of phi, right? So we say, okay, if I have to find the length of the unknown side, I know that the relation between the side of a triangle that is a right triangle is the square of the longest side is equal to the sum of the squares of the two shorter sides. So this is a square of longest side is equal to, this is the sum of the squares of the two shortest sides. Okay? So who is the longest side? 9.00 meters is the longest side. So say 9.00 meters squared is equal to, now what is my one of my shortest side? X. So it's equal to x squared plus, what is my other shortest side? 6. So plus 6.00 meters squared, right? Now, of course, I will solve for x squared, or I will solve for x, right? So I can say now that the square root of 9.00 meters squared minus 6.00 meters squared, that is equal to x, right? Why? Because you subtract 6.00 meters squared from both sides, and later you apply a square root because you have the square. So the only way you can get rid of the square if it's you apply a square root, right? So that means that now when I calculate x, x would be equal to 6.71 meters. It would be really, let me see if it's exactly that value, or it's 9.00 square minus 6.00 square. You know, this is 3 square root of 5, which is, this is 6.70820 meters, right? Now, of course, I cannot leave it like that. Why? Because I have only 3 significant figures in my numbers, right? So I will just express this unknown side with 3 significant figures. So we say that this is 6 point rounding to 71 meters. So 6.71 meters. So now I know that this unknown side is 6.71 meters, right? 6.71 meters. We got it? Now, let's look at, the other two questions. Once we know the unknown side, they ask you to find tangent of theta. Tangent of theta. What angle is theta? This is theta. This angle over here is theta, right? Now, the tangent of theta is opposite side to theta over the adjacent side to theta. The adjacent side to theta. So the tangent of theta is, what is the opposite side to the angle theta? Opposite side to theta is this side. Right? It's the side of the triangle that is in front of theta. Huh? It's the side of the triangle that is in front of theta. Right? Now, what is the adjacent side to theta? This is the adjacent side to theta. The adjacent side to theta is one of the sides of the angle theta. Any angle have an initial side and a terminal side, right? Any angle have an initial side and a terminal side. The adjacent side is always one of the sides of the angle, right? So we have that 6.71 meters would be the adjacent side to theta. So if I want to find the tangent of theta, I would say the tangent of theta is 6.00 meters divided by 6.71 meters. Now, of course, the meters are going to cancel out. Okay? Meters are going to cancel out because the sine, the cosine, the tangent, they have no units, right? The tangent of an angle have no units. The sine of an angle have no units. The cosine of an angle have no units. It's a dimensionless number. It's a dimensionless number. So now when I divide 6 by 6.71, I will get, that the the tangent of theta would be 0.894. 0.894. How many significant figures have 0.894? 3 significant figures. Which are the significant figures of 0.894? The 3 non-zero digits. The 3 non-zero digits. Right? These 3 non-zero digits are the significant figures. Okay? So this is the tangent of theta. Now, next, they want me to find the sine of phi. The sine of phi. Sine of the angle phi. So, the sine of phi would be opposite side to phi over the hypotenuse. Over the hypotenuse. So now, let's see what is the opposite side to phi. So the opposite side to the angle phi is this side. The side with length 6.71 meters. Right? So this side is opposite side to angle phi. So this side, I call this side adjacent side to angle theta. So the side that was adjacent to angle theta, was adjacent to this angle, is now opposite to the angle phi. Angle phi is the angle that is complement of theta. The complement of theta, because we have a right triangle. So the adjacent side to theta is opposite side to phi. And who is the hypotenuse? The hypotenuse is always the longest side. So the hypotenuse is going to be 9. So this sine of phi would be the 6.71 meters divided by 9.00 meters. Of course, we will cancel out the meters because, as I said, sine, cosine, tangent, secant, cosecant, cotangent, all these trigonometric ratios are dimensionless. They are dimensionless. Dimensionless, they have no units, right? This is what dimensionless is. So now when I divide to get the sine of phi, I get that the sine of phi would be 0.746. So the sine of phi is 0.746. And how many significant figures have 0.746? It has 3 significant figures, right? It has 3 significant figures. We got it? So this is, a basic problem of trigonometry, right? Where we had to solve for a triangle to find the length of the unknown side, to find the angle zeta, to find the angle phi, right? Sorry, not the angle zeta and the angle phi. The tangent of the angle zeta and the sine of the angle phi.
Is that 0.74?
Yeah, 0.746, yes. Now, let's solve another problem that involves trigonometry, okay? Let's solve another problem that involves trigonometry. They say a high fountain of water is located at the center of a circular pool, as is shown below, right? Not wishing to get his feet wet, a student walks around the pool and measures its circumference to be 15.0 meters. Next, the student stands at the edge of the pool and uses a protractor to gauge the angle of elevation at the bottom of the fountain to be 55 degrees. So how high is the fountain? So basically, when they say here, how high is the fountain, they want to know this dimension. H. Right? Now, what happens? We don't know the radius. There is a radius here. But this radius is unknown. This radius is unknown. Right? Now, since the radius is unknown, we say, okay, how can we calculate this radius? Oh, we know the circumference. We know the circumference. What is going on? Who is outside? To get a que lo asuste. Do you want me to scare whoever is outside there? Eh? Is it teammate?
Yeah.
Ah! It's fine. All right. Okay, so let's keep doing this, right? So what we know the circumference, right? So now, what is circumference? The circumference is basically this. All this distance around the pool, all this distance, right, is what we call circumference. That is the circumference. So I know that circumference, right? So circumference is equals to 2 pi r. Always the circumference, right, is equals to 2 pi r. So if I know the circumference, I can calculate the radius. And what I want to calculate the radius, because at the end, what I have is a triangle. When I measure the height with a protractor, or when I measure the angle with the protractor, right, I have the angle of elevation. I want to find the height. I need the other side of the triangle. So I need to know, in this case, the radius of the pool. And then if I know the circumference, because I measured it, I can calculate that radius. So if I solve for the radius, I can say that C, which is the circumference, divided by 2 pi is equal to the radius. So the radius will be C. What is C? They say circumference is 15.0 meters divided by 2 pi. This is equal to the radius. So the radius will be, when I calculate that, 2.39 meters. 2.39 meters. That is the radius. So what does that mean? That now I know that I have a triangle like this, where this angle is 55.0 degree. This side, that is the radius, is 2.39 meters. And this other side, that is the height of the fountain, is h, is the unknown side. Is the unknown side. Now, how can I calculate this unknown side? How can I calculate how high is the fountain? So I say, I know this side of 2.39 meters, that is the radius, this side of 2.39 meters is adjacent side to 55-degree angle. And this side of height h is opposite side to 55-degree angle. Opposite side to 55-degree angle. So that means that if I know the adjacent side and the opposite side, I can find easily the tangent of the 55.0 degree angle. So tangent of 55.0 degree angle is opposite side over adjacent side. So the tangent of 55.0 degree is that the opposite side h over the adjacent side 2.39 meters. So if I want to calculate h, I will say h is 2.39 meters times the tangent of 55.0 degree. And with that, we will be able to calculate the value of h. So what is the value of h? Would be, when you calculate that, 3.41 meters. 3.41 meters. That is the value of h. This is how high the fountain is. Look at this one. This one is super interesting. They say vector A has a magnitude of 29 units and points in the positive y direction. when vector B is added to vector A, the resultant vector A plus B points in the negative y direction with a magnitude of 14 units. So find the magnitude and direction of vector B. Okay, let's see a representation of this. Let's represent graphically, you know this. So what I have a vector 8 that points outward, and this vector 8 has a magnitude of 29 units. So we are adding this vector 8 with a vector B that I don't know. I am adding the vector A with a vector B. My vector B is unknown. I don't know the vector B. But later, when I find the resultant between vector A and vector B, I get a resultant vector like this. That is the vector A plus vector B, and it's equal to minus 14 units. The U is U of units, right? This U is of units, right? So let's think about it. Just let us apply the logic to this. I had a vector A that was pointing outward. I had a vector B that I don't know in what direction it points, right? If it points downward or outward, right? But the resultant vector points downward. So vector B must be pointing downward, right? Yes. Now, calculate the magnitude could be problematic, right? When we are just working like that. So what we can do you remember that I mentioned in classes, right, that there is something that we call the univectors. And in the xy plane, we have here one univector that is called univector I, that is in the direction of the positive x-axis. And we have another univector that is the univector J, that is in the direction of the positive y-axis. Univectors are vectors of magnitude 1. So a univector, the only purpose of the univector is to define direction, right? Because the univector have magnitude 1. So the univector doesn't change the magnitude of a given vector. The univector just offers a direction, to a vector that we want to represent, right? So if I rewrite my vector 8 in terms of univectors, or using univectors, I can say that vector 8 is 29, as it points up, univector J. Now, I know my vector B is X, because I don't know its magnitude, univector J. So this is unknown. And I know that my vector A plus B, in terms of the univectors, attendance. So my vector A plus B in terms of the univectors would be minus 14J, because this vector points downward. So it's minus 14J. That means that now when I say vector 8 plus vector B equals vector A plus B, if I substitute, I can say 29J plus xj equals minus 14j. So solving for xj, I can say that xj is minus 14j minus 29j. So xj is minus 14 minus 29 is minus 43j. Is minus 43j. So what it means, right, that my vector b is minus 43j, or I can say my vector b is a vector equal to 43 units downward. So my vector is 43 units downward. If it's minus j means that it's against the direction of univector j. Univector j points up because points in the direction of the positive y-axis. So if I get minus 43j, means that it's a 43, a vector of dimension, of magnitude, 43 units, and what direction? Direction minus j, so opposite to the univector j, so negative y, in the direction of the negative y. Look at this one. They say a roller coaster moved 2.00 times 10 to the second feet horizontally, and then rises 135 feet at an angle of 30 degrees above the horizontal. Next, it travels 135 feet at an angle of 40 degrees below the horizontal. Use graphical techniques to find the roller coaster displacement from its starting point to the end of its movement, right? To find the roller coaster displacement from its starting point to the end of its movement. Now, to do it graphically, to use a graphical technique, I have to do it with a ruler, measuring the length carefully, with a protractor, to measure the angles carefully. So I will represent how we'll do this if we do it graphically, but I will really calculate analytically the magnitude of the resultant and the angle of the resultant. So basically, what they say, and let's do first the graphical representation of this, right? They basically say this. They say, oh, I have a roller coaster that is moving 2 times 10 to the second feet horizontally. So this is a displacement. So 2.00 times 10 to the second feet, that is what we call displacement. Displacement is a vector. Remember, distance is not a vector, displacement is a vector. So I am moving horizontally like this. 2.00 times 10 to the second, this is the same as 200, because this is 2.00 times 100. This is 200 feet. Horizontally, right? Now later, it will be moving 135 feet at an angle of 30 degrees above the horizontal. So if I extend this line that is the horizontal, now I have that there is a vector of 135 feet like this. There is an angle of 30 degrees above the horizontal. Right? That was my next displacement, right? 135 feet at an angle of 30 degrees above the horizontal. Now, I will just show the horizontal here again, because now I have 135 feet and an angle of 40 degrees below the horizontal. Below the horizontal, but 40 degrees below the horizontal. So this here would be 40 degrees, and these are 135 feet again. So at the end, the resultant vector, we go from the tail of the first vector of 200 feet horizontal to the arrowhead, to the head of the 135 feet vector that was 40 degrees below the horizontal. So if I want to find the resultant vector, I have to join these 2 points. This should be the resultant vector. Now, what is the magnitude of this resultant vector? What is the angle of this resultant vector? Of course, it looks like this vector will be below the horizontal, right? Because we have an angle here, theta, that looks like it's below the horizontal between the vector. Let me see if I can maximize this a little bit. There is an angle theta between the vector resultant and the horizontal. Now, how can I calculate that? To do it graphically, I have to have ruler, protractors, I have to measure everything carefully. So it's very difficult to do it graphically. Now, how we can do it then analytically, right? So what we can do analytically, I can say, okay, let me make a coordinate system here with x and y. And then let me represent my vector of 200 feet horizontal here. So this is my 200 feet vector. What else? I will represent my vector of 135 feet, 30 degrees above the horizontal here. Oh, this is too much. Wait. I will represent now my 135 feet vector, 30 degrees above the horizontal. And I will represent my 135 feet vector 40 degrees below the horizontal. Now, all these vectors are pointing to the right. So the horizontal component of this vector will go to the right. So the vector of 135 feet and 30 degrees above the horizontal. And the x component of the vector of 135 feet and 40 degrees below the horizontal, all these vectors will have the x component pointing to the right. You make a projection of all those vectors on the x-axis. The component is to the right. The x component is to the right. So how do you calculate the x component? R sub x, the resultant in the x-axis of all these vectors. The 200 feet vector is horizontal, so I don't have to find any component for this. Now, the 135 feet above the horizontal, its x component would be a projection of this 135 feet vector on the x-axis And when you make a projection of that vector on the x-axis, that projection looks like this, right? And this projection, if this is the angle of 30 degrees, this projection will be 135 feet as its adjacent side to 30 cosine of 30 degrees. So you say plus 135 feet cosine of 30 degrees. Now plus, then you have this other vector that is 40 degrees below the horizontal. So now, how that vector below the horizontal, how do you analyze it? You say, oh, this vector below the horizontal that I'm representing here with the green color at 40 degrees, when I make a projection on the x-axis of this, right, I will get now my component, right, that I will say there is this one. And this component will be the x component, again, 135 feet, in this case, cosine of 40 degrees, because this angle is now 40 degrees for the vector below. So I say plus 135 feet cosine of 40 degrees. So with that, you can find your r sub x. And your r sub x will be, when you calculate this, 420.33 feet. I will round at the end because I want to express at the end, my result with 3 significant figures, right? So I will round this at the end. I will find out r sub y. R sub y, the y component of these vectors, the vector of 200 feet is completely contained on the x-axis, so we have no y component. If you make a projection of the red vector on the y-axis, it's a dot. So there is no line, right? There is no component on that axis because it's completely horizontal. So you are contained completely on one axis, you have no component in the other. Now, the vector of 135 feet with 30 degrees above the horizontal, we have a component here that will be this one, pointing outward. And that component pointing outward will be by the sign. So it will be 135 feet sine of 30 degrees. 5 feet sine of 30 degrees. And then this other vector that you see here, that is 135 with 40 degrees with respect to the horizontal, we have also a y component, but its y component point downward. When you make the projection, it points downward. So this is 135 feet sine of 40 degrees. So you have one vector pointing outward, that is this one, and you have this other that points downward. So when you find r sub y, we are taking the one pointing outward positive. I say this is 135 sine, 135 feet, 135 feet sine of 30 degrees minus 135 feet sine of 40 degrees. So this one that is the one pointing outward minus this one that is the one pointing downward. Now r sub y will be, when you calculate that, you get minus 19.20, sorry, 19.28 feet minus 19.28 feet. Now, what that means, that these three vectors give you as resultant one vector here, that is horizontal and have 420.33 feet, and they give you a y component here that is this vector of 19.28 feet pointing downward. When you will find the resultant of the two vectors, you use the method of the parallelogram, and then you can join them. You can join these tails with this intersection, and this will be the resultant vector. Remember that this one is r sub x, the resultant in x, and this one is the resultant in y. So the whole resultant will be the using the Pythagorean theorem will be the square root of the square of this value plus the square of this other. And the angle that you will have in this case is this one, and we call this angle theta. So if I want to find the whole resultant, I will say that the resultant is the square root of this 420.33 square is in feet plus 19.28 square is in feet. So when you feet and feet square, if feet squared, square root of feet squared will be feet. So you will get now that this is approximately 421 feet. Now you calculate also the angle theta, this angle that I show you over here. That is the angle of the resultant of the three vectors with respect to the horizontal, and it's below the horizontal. And that angle is the tangent inverse of the y component, there is 19.28 feet, divided by the x component, right? It's always delta y over delta x, so it's just 420.33 feet. So zeta would be, when you find that tangent inverse, is 2.63 degree that you can approximate to approximately 3 degree below the horizontal. Below the horizontal. Yes. A motorist drives north for 35 minutes at 85 kilometers per hour, and then stops for 15 minutes, and then he continues north traveling 130 kilometers in 2 hours. So they say, what is his total displacement and what is his average velocity? So now remember that the total displacement, the displacement is a vector, right? So remember that. Displacement is a vector. Okay? The displacement is a vector. And the displacement delta x is x final minus x initial. This is what is displacement. X final minus x initial. It's open now. Now, average velocity, remember that average velocity would be, in this case, the variation is also a vector, and the average velocity would be the variation of displacement over the variation of time. So it will be x final minus x initial over t final minus t initial, right? This would be the average velocity, right? So the first thing we're going to do is to find the total displacement. So we have first this guy driving 85 kilometers per hour during 35 minutes. So during this time, he was able to travel, a distance of d1, right? So he travels a distance d sub 1 during these 35 minutes at 85 kilometers per hour. Then he stopped for 15 minutes. In this case, there is a second distance that is 0 because he stopped for these 15 minutes, right? As he stopped for 15 minutes, during that time, his displacement was 0. And then later, we have that he's traveling 130 kilometers in 2 hours. But here is given the distance that he traveled, right? So what we don't know here is the velocity, but we know the distance that he traveled. So this number is d sub 3. So to find the total displacement, I have to find then d that is equal to d sub 1 plus d sub 2 plus d sub 3. So the d sub 1, as we don't know d sub 1, it would be displacement is velocity times time. Displacement is velocity times time, right? So I have to get its velocity, and I can calculate the displacement if I multiply this velocity times the time. So what is the velocity? 85.0 kilometers per hour, and the time is 35 minutes, but I cannot work with minutes and hours. So I need to, in this case, convert those minutes to hours. So I can say I will multiply times 35 minutes times 1 hour every 60 minutes. And like that, I can cancel out the minutes here. I can cancel these hours with hours, and I will get my displacement in kilometers. So that means that I have to multiply 85 times 35 and divide that by 60, right? Because like that, when I do this 1 hour over 60 minutes, what I'm doing is converting the 35 minutes into hours in order to cancel the hours of the kilometers per hour, right? I cannot cancel minutes with hours, right? That's why I have to do this conversion here. Here I am converting minutes to hours. So what is this sub 1 then? We get that this sub 1 would be, when we do these calculations, 49.58, so 49.6 kilometers. 49.6 kilometers. So that means that now I have that the distance d, or the displacement d in this case, is the first 49.6 kilometers that is what he traveled during this time, right? When he traveled at 85 kilometers per hour during 35 minutes, he travels just 49.6 kilometers plus 0 kilometers 0 kilometers during these 15 minutes that was resting, right? That just was in the stop, plus then the 130 kilometers in the last 2 hours. So in total, we get 179.6, this is kilometers, 179.6 kilometers. Which is approximately 180 kilometers. So this was the total displacement. Now, why I am just adding? Because displacement, I said, is a vector, because he's driving north during the first part of the trip. So this first displacement is north, right? Look at this, north. And what happened later? He continues north. So the tree is also north. So it's also north. So the displacement D, that is D sub 1 plus D sub 2 plus D sub 3, as it was always north, I am just adding, you know? So my total displacement D, right, is 100 kilometers north. North of the origin, at whatever city or town it was, when he's driving north, at the end, after all this time, it would be 180 kilometers north of the origin, right? Now, this is the total displacement. How do you calculate now the average velocity? So remember what we said. The average velocity is the total displacement, you know, or the variation in position, which is the displacement, delta x, over the variation of time. Now, in this case, we have to consider also the 15 minutes the guy was, you know, resting. So when you calculate now this, you will have, it was just 15 minutes, 15 minutes is 0.25 hours. So now, when you will calculate the average velocity, you say, okay, is my displacement of 180 kilometers, right, divided by now all these times. So 35 minutes. Remember that to convert 35 minutes to hours, because we want the average velocity in hours, in kilometers per hour. So you say 35 minutes times 1 hour in 60 minutes, plus, now what else? 15 minutes times 1 hour in 60 minutes, plus 2 hours. So this one is already in hours, right? So you will simplify here. When you divide 35 by 60, you will get time in hours. When you divide 15 by 60, you will get a time in hours. You have the numerator in kilometers. You have your denominators in hours. What is the output? Kilometers per hour, right? So when you calculate that in kilometers per hour, this will be at the end that the average velocity was 63.4 kilometers per hour. So this is an example, you know, of an exercise where we apply, in this case, the concept of total displacement, and average velocity, right? This is part of the second topic that was about motion in one dimension. Now let's do another exercise. That is the exercise number. They say that a certain car is capable of accelerating at a rate of 0.6 meters per second. So how long does it take for this car to go from a speed of 55 miles per hour to a speed of 60 miles per hour? Now, what problem we have here? We have the acceleration, so let us see the norms and the unknowns. Always in the problems of physics, it's good to find the norms and the unknowns. So what I know that it's able to accelerate at a rate of 0.60 meters per second squared. So I know acceleration. There is 0.60 meters per second squared. Now, what else? They say, how long does it take? So how long is asking about time. So we don't know the time. So time is unknown. The time t is an unknown. Now, how long does it take for this car to go from a speed of 55 miles per hour from this speed to 60 miles per hour? So what speed is this one? The initial. What speed is this other? The final, right? So we have an initial of 55 miles per hour to a final of 60 miles per hour. Okay? So I know initial speed B initial equal to 55 miles per hour. And we know final speed final. So let me fix this. It looks like a final speed. Come on. Which is B sub F and is 60 miles per hour. Now, I know now the norms and the unknowns. What formula relates the norms and the unknowns? What are the formulas of kinematics? And this is how the reasoning must be done, right? You start reading the problem. You start finding which are the norms and which are the unknowns, right? And then you say, okay, what is the formula that can relate, what is the equation that can relate these norms with these unknowns? Well, there is one that we know that say that B final is equals B initial plus acceleration time, right? There is one formula that just looks like this that relates final speed, initial speed, acceleration, and time. Now, what problem I have? I have a problem here, and it's a problem with the units. It's a problem with the units. Why I have a problem with the units? In what units is given my acceleration? In what units my acceleration is given? Look at the screen. In meters per second square. But in what units my velocities are given, my speeds are given? In miles per hour. I cannot operate with miles per hour and meters per second squared together. So I have to do something that is convert the miles per hour into meters per second. I will convert my miles per hour into meters per second. I have to do that. If I don't do the conversion and I try to do my time calculation with those units that are given, you have seconds squared in the acceleration and you have hours in the speeds. What final unit of time you get? You have seconds and hours. So it's going to be a mess. The value that you're going to get is going to be a real mess, right? So that's why you have to do the unit conversion first. When the units are basically the same, when the units are just, let us say, like coherent, because you have, okay, my speed is in meters per second, my accelerations are in meters per second squared. Okay, I know that if I calculate the time, I will get my time in seconds. But now, I have my acceleration in meters per second squared, and I have my speed in miles per hour. I have two different units of time. What is the unit of time that I will get? Seconds or hours? I don't know, because we cannot combine those units. So that's why it's important now to say, oh, okay, before doing anything, I will convert my 55 miles per hour into 55 miles per hour into meters per second. Now, I gave you before the conversion factors. So I said that 1 mile is 1,609.35 meters. So I can say times 1,609.35 meters that I have in each mile. Like that, I can cancel the miles out and I get now meters. Now, but also I have to simplify the hours. So I say 1 hour that have 3,600 seconds. Like that, I can cancel the hours out. So I will multiply 55 times 1,609, and I will divide that number by 3,600. And like that, my initial speed, v sub I, will be in meters per second. When I do that, I get v sub I equals to 24.6 meters per second. 24.6 meters per second. Now, let me get now B sub F, B final. So B final will be my 60 miles per hour times. I have now to convert the miles to meters. We say 1,609.35 meters in each mile times then 1 hour, in 3,600 seconds. So I cancel the hours out, I cancel the miles out, and then I can just get now my final speed in meters per second. And my final speed in meters per second would be 26.8 meters per second. Once I have my initial and final speed in meters per second, now my units are coherent, right? All my units now are similar, right? So I can cancel the meters, I can operate with the seconds, I will get my time in seconds, So I say, okay, what is next? I have to solve for time. So if I have B sub F equals B initial plus AT, right? I will be subtracting now B initial, so say BF minus B initial is equal to AT. I want to calculate T, so we divide by the acceleration. So I say B final minus B initial divided by the acceleration is equal to t. So t will be equals to, what is my b final? 26.8 meters per second. Minus, what is my b initial? 24.6 meters per second. Divided, what is my acceleration? 0.6 meters per second squared. I'm sorry. So what is now the time? The time would be, subtract here, divide by 0.6, it will give you 3.72 seconds, or 3.7 seconds, basically. 3.72 seconds or 3.7 seconds, right? So this is what takes, for the car to go from 55 miles per hour to 60 miles per hour if the acceleration rate is 0.60 meters per second squared. Now look at this. One more to get a break and come back and keep doing more. So, hey, hello, please, hey. Okay,